Simplifying High-Performance Computing Architectures, An Engineering Perspective by Patricia Florissi. High-performance computing architectures, or HPC architectures for short, have been designed to address the needs of very computationally intensive applications. Consider, for example, a scientist that needs to understand the dynamics of the ocean currents in order to predict where oil spills will flow and be able to accurately direct response crews. Typically, scientists analyzing complex systems cannot measure and understand them in the real world because it's either too expensive, or it is too dangerous, or there are no instructions or devices that allow a measurement with the precision required, or all of these reasons combined and more. Scientists then have no other option but to design an intricate set of mathematical models that create an approximate simulation of how the different components of the system behave and how each one of them depends on each other. Climate modeling, for example, typically requires coupled simulation of several interrelated models, such as atmospheric, sea ice, and ocean modeling. Each one of these models exhibits so much complexity that a full ocean modeling at even a 1,000 feet resolution requires billions of computational cycles. Sometimes, these systems model decades of real time, and the entire simulation may take 100,000 hours of computation or more, and by then, any disaster response may be just too late. HPC architectures are designed to improve execution time by partitioning the execution into smaller pieces and computing the pieces in parallel. In the ocean current case, for example, if the simulated space can be partitioned into 10,000 space fragments, and each one of them can be individually simulated in parallel by 10,000 compute nodes, the simulation will run in just 10 hours. The secret, not so secret, about partitioning simulation models is that the partitions become very tightly coupled, meaning that the fragmented simulated spaces turn out to have a high degree of dependency and relationship with each other. In other words, a change in one simulated space fragment may propagate changes on the adjacent simulated space fragments, which may in turn propagate to its adjacent space fragments, and so on and so forth, just like a ripple effect. This interdependence then imposes a requirement on the compute nodes to communicate often, very often. In the ocean current simulation, for example, a node may need to indicate when water has flown from its simulated space into an adjacent simulated space. Similarly, tightly coupling may exist when partitioning the simulation space for other scientific computations, such as a model for the collision of particles and the interaction of condensed matters in physics experiments, or a model for the molecule pathway during the human metabolic process, or a model for seismic movements of the layers of the Earth. In fact, the whole rationale used for a simulation of the ocean is not very different at all from the simulation used by animated movies, which require an immense ability to manage the complexity and interdependencies among the several regions of a drawing to accurately model human quality movement, shadow casting, highlighting of areas, and light and shade manipulations. And so, HPC architectures emerge. HPC architectures typically consist of a massive number of computing nodes, typically in the order of thousands of them, which are highly interconnected via a specialized low-latency network fabric. This fabric implements InfiniBand or uses proprietary interconnects specialized for internode communication, on top of which the nodes will deploy a message passing interface, or MPI for short, for data exchange. The computing nodes are also connected to a set of storage nodes via a secondary storage network designed for high bandwidth. In some architectures, the compute nodes connect directly to the storage system, building a fully connected network design, often referred to as a fat tree. Other architectures use, instead, a relatively small number of specialized nodes called I/O nodes. These I/O nodes are then placed at the edge between the two networks and route storage I/O between the compute nodes and the storage system, becoming a less costly option. By using network subnets and storage routing, the I/O nodes save money by splitting the fat tree into several slender trees and reducing the total number of branches and roots. On the processing side, each compute node consists of a set of core processors and lots of main memory to store the initial data to be analyzed, the intermediate values created during the computation, and the data generated as a result of the computation. In some rare scenarios, the computing nodes also contain a boot disk containing the minimal information required to initialize and manage node operations. Since mechanical devices fail too frequently, and failure of any one compute node will interrupt the entire execution, compute nodes typically boot over a network storage disk. And by now, you may be wondering, what is the most powerful, the fastest computer out there? Well, that actually is an easy question to answer, as it turns out. You see, the website www.top500.org publishes twice a year a list of the 500 fastest supercomputers in the world. According to the site, as of November 2011, Japan's K-computer maintained its position atop of the top 500 list of the world's most powerful supercomputers, being 4 times as powerful as its nearest competitor. Installed at the Riken Advanced Institute for Computational Science, AICS, in Kobe, Japan, the K-computer achieved an impressive 10.51 petaflops per second on the LIMP-PAC benchmark. And yes, you heard it right, 10.51 petaflops. That's 10.51 thousand trillion floating point operations per second. Wow! Well, one of the secrets, not so secrets, about HPC architectures is that it achieves petaflop scale performance through parallelization. The question is, how is it different, however, from parallelization in a cluster architecture using a Hadoop framework, for example? It's important to remember that in a Hadoop-like cluster architecture, it all starts with a node consisting of a set of commodity processing cores and main memory attached to a set of commodity disks. Then a stack of nodes forms a rack, and a group of racks form a cluster, all connected via a high-speed network to enable fast exchange of information. These cluster architectures have been designed for shared nothing, massive parallel processing type of applications, where parallelization is achieved by partitioning the data equally among the nodes and by benefiting from the principle of data locality, where the data can be processed by the computing cores co-located in the same node or at least in the same rack as the disks where the data is. Data locality tries to minimize data transfer across the nodes. A shared nothing architecture assumes that the nodes can execute independently without much communication up until the end of the execution and are fit for applications considered to be embarrassingly parallel. HPC applications, on the other hand, parallelize a job by dividing the computation into tasks and distributing these tasks across the nodes. Unlike in a shared nothing architecture, the data is very tightly coupled, and the parallel tasks need to constantly synchronize their execution and exchange information, repeating this pattern several times per second. It is important to note, however, that there is one principle common to both architectures: the goal to minimize the amount of time that computing nodes are idle while waiting for other nodes to finish, even though they use very different approaches to achieve the common goal. In a shared nothing architecture, the data is partitioned into chunks of the same size, assuming that the time it takes to process an equal-sized chunk of data is the same for every node. In an HPC architecture, however, the computation is divided into tasks that takes approximately the same amount of time to execute. In fact, the tasks may be the same or not, may process the same amount of data or not, but it is assumed that each task takes approximately the same amount of time to execute. Any time a node spends idling waiting for other nodes to finish is referred to as an execution jitter or noise, and you better believe that these jitters cost a lot in execution time. Computational intensive applications running on HPC architectures actually exhibit a very distinct life cycle consisting thousandths of times a second until the whole computation ends. Finally, during the data offloading phase, the computing nodes transfer the results from main memory into the storage. The data loading and offloading phases are typically very, very small, in order of hours when compared with the entire computational cycle, which may last weeks, months, or even years. HPC architectures are then optimized to reduce the computational time by adding more compute nodes, and leading to a multi-million-dollar computing architecture, which can be extremely high-performing for certain applications, but that it is still very much prone to failures. In fact, today, a machine with 1 million CPU cores is considered as a whole system to remain completely functional for a day. After that, at that scale, failures are inevitable. If you fast forward to tomorrow with 1 billion cores, the whole system is likely to only be functional for an hour. Now, imagine a computation task which can take months or even a year to complete on a system which is functional only for 1 hour at a time. And that's where the concept of resilience comes in. Resilience refers to the ability of continuing executing operations in the presence of system component failures without requiring to start in the operation from the beginning. In a tightly coupled application, the failure of a single compute node causes the entire execution to fail. Today, resilience is added by periodically saving the entire memory state of the system in disk, forming a checkpoint. So when the inevitable failures occur, you can simply reload the checkpoint and continue from there, not from the beginning. Checkpoints may actually have a dual purpose, serving not only to add resilience, but also as a snapshot of a point in the history of the computation. Consider, for example, at a given point during the execution that a range of values can be applied to the next cycle as simulation parameters. A scientist may decide to make a checkpoint referred to as a historical checkpoint, apply a given set of values to the simulation variables, and continue execution. At a later point, the scientist may decide to go back to the historical checkpoint and then resume the execution, but this time around with a different set of values. The ability to have historical checkpoints allows the exploration of several execution paths without forcing the computation to start from the beginning every time. Now, there are good news and not so good news. On the good news front, should a node fail, the system can restart from the last checkpoint. On the not so good news, checkpoints take time away from execution, and in large scales, this may mean a lot of time away, since you may need to save hundreds of terabytes in a matter of minutes, and it may require to scale to saving hundreds of terabytes or even petabytes in a matter of minutes. And that's when HPC architectures started increasing the level of parallelism to the data transfer itself. This is a very important and intriguing concept, and close attention must be paid here. During data transfers, the thousands of compute nodes are busy transferring data instead of being busy computing the next cycle. And that comes at a high price. And to complicate matters even further, the high volume of data imposes severe bandwidth demands. So to make this example even more concrete, let us go back to a typical HPC example that generates 300 terabytes of data each checkpoint, and let us do some real math here. If a disk does 100 megabytes per second, then 10 disks will be able to do 1 gigabyte per second. Since 1 terabyte has 1,000 gigabytes, a single storage node will need 1,000 seconds per terabyte. In order to save 300 terabytes through a single storage node, that will take 300 times 1,000 seconds for 300 terabytes, which is equal to 300,000 seconds to save the 300 terabytes. Now, 300,000 seconds divided by 60 seconds is equal to 5,000 minutes. 5,000 minutes divided by 60 minutes per hour is equal to approximately 83 hours, which is approximately 3.5 days per 300 terabyte checkpoint. But luckily, we can afford more than one storage node. So if we use 10 storage nodes instead, then it will take 30,000 seconds. And if we can deploy 100 storage nodes, it would take 3,000 seconds. And if we can deploy 300 storage nodes, it would take 1,000 seconds, which is less than 17 minutes, or 16.66667 to be more precise. Amazing, right? And that's exactly when a trend began in the HPC world. Architects started designing architectures where more storage nodes were bought, not because of the need to increase capacity, but because of the need to increase performance, as measured by the aggregated I/O throughput. Increase the storage node performance meant reduce the checkpoint time, which meant increased overall system resilience. Beautiful, really, right? But hey, stop! Are you not forgetting something? What is wrong with this equation? I'm afraid to ask. Well, what about, let us say, big data? Don't you think you must factor that in? Consider the 2015 Department of Energy, DOE for short, supercomputing challenge, where they will generate between 3 to 5 petabytes per checkpoint, and they cannot afford to spend more than 20 minutes to save it. And why 20 minutes, you may ask? Well, the math is quite simple, actually, and yes, we will go through it together right now. The DOE needs a checkpoint every 3 hours in order to ensure sufficient progress in the face of inevitable failures. And if they want to maintain a 90% machine utilization rate, they can only spend about 10% of the time checkpointing. 3 hours is equal to 180 minutes, and 10% of 180 minutes is 18 minutes, which we have graciously rounded up to 20 minutes. Get it? So instead of deploying 300 storage nodes, the DOE will need to deploy 3,000 storage nodes to keep the same 17 minutes checkpoint performance. And what about future challenges generating not 3, but 30 petabytes of data every checkpoint? Will the DOE be able to deploy 30,000 storage nodes instead? When it comes to exascale, buying storage for performance and not for capacity becomes exorbitant. Get it? In essence, this equation, I'm afraid, is not big data proof. Plus, tomorrow, with exascale systems being scaled up by a factor of 1,000 times, and therefore reliable for shorter periods, we are going to need a shared storage system that can take a much, much larger memory state dump, about 1,000 times larger than today, and be able to save that entire system state in about 100 seconds. So it is 1,000 times bigger and 10 times faster. How big is this? Think of a system that can handle a 100 terabyte per second bursts, or 30 petabytes burst in 5 minutes every 1 hour, and be able to store 900 petabytes of checkpoint space. And that's where Flash comes to the rescue. Flash technologies make possible to extend HPC architectures in many creative and innovative ways to deliver high performance and in a manageable, automatable, and sustainable way. And that's why you need to listen to the next Big Ideas video on demystifying fast data to learn more about how to really harness the value of adding Flash technologies to HPC architectures. And more importantly, to understand how EMC, being at the intersection of cloud and big data, is strategically positioned to empower you to obtain this value in the most effective manner.